Welcome everyone to our ISSI-BJ on Things to Come online seminar. If you followed our previous webinars, you more or less now know what it is about. We have started this webinar series last year in September, where we try to focus on ongoing and future space missions from different agencies all over the world. We have, of course, the European Space Agency, the Japan Aerospace Exploration Agency, we have NASA, and we invite guest speaker, outstanding scientists working on these space missions to present the mission and accept questions from the audience to try to enlighten us about the missions. And we have today Professor Yoshifumi Saito. Thank you for accepting our invitation, who will talk about the BepiColombo mission to Mercury of the European Space Agency and the Japan Aerospace Exploration Agency. This is the fourth webinar on this mission, the fourth and last one, because we've tried to focus in detail on the mission and present it in the best way possible. And very briefly about ISSI-BJ, for those who are not familiar with the institute, it was founded in 2013 thanks to the cooperation between the National Space Science Center of the Chinese Academy of Sciences and the International Space Science Institute in Bern, Switzerland. And ISSI-BJ, like ISSI in Switzerland, we aim to advance space science studies. So we aim to support scientists from all over the world to carry out their research either here at our premises or elsewhere, but thanks to our support, and also because of these and because of the pandemic that didn't allow us to organize any offline event at ISSI-BJ last year, we have started this online seminar series. We also have another seminar series which is in Chinese and which is called 1001 Space Night. We will have next one next Monday. But without any further delay, I will ask Professor Ip, who you can see here, he's the Executive Director of ISSI-BJ, to introduce our speaker. And thank you once again for being here.
Yes, thank you, Lola. So today we have Professor Yoshifumi Saito to give this the number 4 talk on the BepiColombo mission, which is a cooperation between ESA and JAXA. A few words about Professor Saito. For me, he is just a baby, you know. Much younger than I am, and he got his bachelor degree in Tokyo University and got his PhD degree in Tokyo. And you will hear from him. You know, he's an expert on space plasma physics, but most importantly for us, he is a wonderful experimentalist, and he has a magic finger in building instruments. And so he had been involved in the plasma instrument on Kaguya, and who have made many interesting discoveries. And now he will be telling us what he's going to do with the plasma instrument on the Japanese spacecraft on BepiColombo. Yeah, Saito-san, please start your talk.
Okay, thank you very much, Bing-san. And I will share my screen. Okay. Okay, can you see my screen?
Yes. Yes.
Yes, we can see the screen. Yes.
Okay, thank you very much. Today, I will talk about Mercury Plasma Particle Experiment, MPPE, on board MEA spacecraft. And I'm Yoshifumi Saito from ISSI-JAXA. Okay, I'm a PI of the MPPE instrument on board MEA. Okay, because the previous speakers already talked about BepiColombo mission itself, I will not go in detail, but briefly review this mission. And the BepiColombo was launched on 20th October 2018 by Ariane 5 launch vehicle. And on the rocket, the 2 spacecraft were on board, and MMO and NPO. And MMO is developed in ISSI-JAXA, and NPO is developed in Europe. And after the launch of the spacecraft, BepiColombo will experience 1 Earth flyby and 2 Venus flybys and 6 Mercury flybys before arriving at Mercury in December 2025. And after arriving at Mercury, MMO and MPO are separated, and MMO's orbit will be 590 kilometers times 11,600 kilometer elliptical orbit with its orbital period of 9.3 hours. And MPO has the orbit of 480 kilometers by 1,500 kilometers, and the orbital period is 2.3 hours. And its two spacecraft will make observation of Mercury at least for 1 Earth year. And BepiColombo consists of 4 components. One is MEA spacecraft developed in ISSI-JAXA. This is Mercury Magnetospheric Orbiter, previously called MMO. And Magnetospheric Orbiter Sunshield and Interface Structure, MOSIF. And Mercury Planetary Orbiter, MPO, developed by ESA. And Mercury Transfer Module, MTM. And during the cruising phase, these 4 components are stacked together and go to the Mercury. This figure shows the MEA spacecraft. The left-hand side big photo shows the MEA spacecraft in ISSI-JAXA, and these two figures shows the MEA spacecraft in operation. And we can see high-gain antenna here, and 2 deployable masts, and magnetometer is installed on that, and 4 wire antennas, 5 meters long. And we can see some particle detectors shown by this white color. And also we can see middle gain antenna here. And the surface of the spacecraft is mirror finished in order to reflect or reject the intense solar radiation at Mercury orbit. Okay, and this table shows the MEA instruments. MEA has 5 major instruments: MPPE, MGF, PWI, Musashi, and MDM. And these 3 instruments, MPPE, MGF, PWI, is a complete package to measure plasma environment. And using these instruments and with MPO, we will make complete measurements of Mercury's environment. Today's my talk is dedicated to this MPPE instrument. And MPPE is Mercury Plasma Particle Experiment, and it is a comprehensive instrument package to make measurements of ions and electrons in the solar wind and in the Mercury's magnetosphere, and neutral particles from Mercury's surface. And MPPE consists of 7 sensors. The photos are here: MIA, MEA1 and 2, and MSA, and HEP-ion, electron, and ENA. And more than 1,000 members are participating in this experiment from Japan, Europe, USA, Taiwan, China, and Russia. And this figure shows the MPP sensors. We have totally 7 sensors, including 2 MEAs. MEA is Mercury Electron Analyzer, which measures energy spectrum of electrons between 3 eV to 26 keV. And MIA is Mercury Ion Analyzer. It measures energy spectrum of solar wind ions between 100 eV per charge to 29 keV per charge, and energy spectrum of Mercury ions between 15 eV per charge to 29 keV per charge. And MSA is Mass Spectrum Analyzer, and it measures energy mass spectrum of ions between 1 eV per charge to 38 keV per charge, and mass range between 1 and 60, so hydrogen to iron. And HEP-ion is the high energy particle ion sensor detectors, and it measures energetic ions between 30 keV and 1.5 MeV. And HEP-electron measures high energy particle electrons, and it measures energetic electrons between 30 keV and 700 keV. And ENA is energetic neutral atom, and it measures low energy energetic neutral atoms between 10 eV to 3.3 keV. And this figure shows the MPP sensors on MEA spacecraft. Looking from the top side, all the MPP sensors are installed on the side panels. And 4 low-energy sensors, MEA1, MEA2, and MIA and MSA, are installed at the corner of the octagonal spacecraft. And HEP-electron and HEP-ion and ENA are installed on the spacecraft panel. And okay. And this figure shows the field of view of the MPP sensors. MIA has the ring-shaped field of view, and MEA2 also has a ring-shaped. And MSA and MEA1 also has ring-shaped field of view, but one side is blocked by these masked structures. So in this figure, only one side field of view is shown. And the spacecraft spin rate is 4 seconds. So the time resolution of these instruments to obtain 3-dimensional electron and ion distribution function is 2 seconds. But using the one set of low-energy electron analyzers, MEA1 and 2, and one set of ion analyzers, MEA and MSA, we can obtain the distribution function of electrons and ions with time resolution as high as 1 second. However, because one side of the analyzer is blocked, the coverage is about 3/4 of all the hemispherical field of view. Okay, and this figure shows the field of view of HB electrons and HB ion sensors, and also ENA analyzers. Okay, and on the spacecraft, we have 3 different data rates: high, medium, and low. And MPP sensors, for MPP sensors, these data rates are allocated. For high mode, 72 kilobps, for MEA, MIA, MSA, and HEP. And for M mode, 6.65 kilobps are allocated. And for L mode, 0.8 kilobps are allocated to all the analyzers. And L mode data are 24-hour continuously available. And using this data mode, MEA and MIA and MSA, these are called low-energy particle sensors, will measure velocity moments of electrons and ions, including density, velocity, temperature, and compressed ET spectrograms with limited angle, mass, energy, time, and time resolution. And high-energy particle sensor measures count data with limited angle, mass, and energy. And ENA produces only L mode data. And concerning the M mode data, this is 25% of all the periods available for during 25% of all the period. And using this data mode, 3D counts with selected angle and time resolution of 2D counts or 2D counts are obtained. And H mode data is only available during limited period. And but using this mode, full 3D counts are obtained. Okay, and this figure is very complicated, and this table shows the data product of MPPE, especially for MEA, MIA, MSA, and HEP sensors. And in order to limit the data rate, we defined the 6 observation mode for MPPE. And these modes are default observation mode, exospheric mode, and solar wind mode, and IP shock local mode, and IP shock macro mode, and bow shock mode, and reconnection mode, and magnetospheric mode 1 and 2 and 3. And by defining this data mode, in each MPP operation mode, each sensor is switched to its own observation mode, and the total data rate is within the allocated data rate. Okay, and before talking about in more detail about each instrument, I will talk about the science objectives of MPPE. And I think this figure was already shown by Murakami-san 2 weeks ago, but this figure shows the Mercury's magnetosphere. And Mercury's magnetosphere is closest to the sun and exposed to the strong solar wind. And Mercury has weak magnetic field, but intrinsic global magnetic field, and it is drastically affected by solar wind. So Mercury it can be said as an extreme environment to study the dynamic interactions. And this figure also shown by Mercampson 2 weeks ago. And this figure shows the MU's target, Mercury's environment. And Mercury has no atmosphere, and direct interaction between solar wind and surface is expected. So these regions, solar wind and magnetosphere, exosphere, surface, and also interior are, well, interacting with each other. So what we have to answer is to the question, how does solar wind control Mercury's environment? We have to answer to this question. And this table shows the targets of MPPE observations. It includes solar wind and magnetosphere and exosphere and magnetosphere surface coupling. And talking about solar wind, we are very interested in bulk shock or interplanetary shock or solar wind properties and so on. And concerning magnetosphere, we are very interested in magnetopause induction and Helmholtz waves and substorm activities, including FTDs and dipolarization. And also we are interested in high energy electrons and also X-ray aurora that may be caused by electron precipitation, and field and current system that reflects the surface interior conductivity. Okay. And I will show you three major objectives of MPPE. And one is a dynamic magnetosphere substorm. And thanks to the messenger observation, in Mercury, many FTEs are found. For example, 163 FTEs along 10 magnetopoles in 25 minutes. And also substorm-like events are also found in Mercury, and it is Earth-like, but the time scale of the substorm is very short, as short as 1 minute. So what we have to do is to make high time resolution measurements. And MPPE, including MIA, MSA, and MEA, will make high time resolution measurements of ion and electron distribution function related with substorm and FTEs. By doing so, we want to understand the Mercury substorm mechanism. And next is X-ray aurora. And this is a very interesting phenomenon discovered by a messenger spacecraft. And it is an X-ray fluorescence on the night dawn side. And it is also found that induced by electrons higher than 4 keV. And event detection is about 30% of messenger orbits. And we have to answer to the questions that solar wind affect the X-ray aurora, or why are they observed on the night dawn side? And we have to understand if there are any relation with the exosphere. So what we want to do is that MMO MPPE, HEP electron, and MEA will make measurements of low to high energy electrons equally between southern hemisphere and northern hemisphere, while MPO measures X-ray from Mercury surface. So MMO MPPE MSA will also measure exospheric ions with high mass resolution. And by doing so, we want to understand the generation mechanism of this X-ray aurora. And the third one is the sodium atmosphere. This figure shows the subsolar sodium signals under interplanetary coronal mass ejections. And ground-based observed sodium distribution is shown here. And the distribution is different between the quiet time and coronal mass ejection hits the Mercury. And what we want to do is to, MPPE, MIA, and MSA will make direct measurements of the cusp precipitating ions and ions generated by precipitating ions around cusp. And MPPE-NA will all measure neutrals. And by doing so, together with MPO, we'd like to understand the generation mechanism of sodium atmosphere. Okay, from now, I'll talk in more detail about each instrument of MPPE. First one is MEA. This is a toroidal electrostatic analyzer with electrical sensitivity control. And MEA measures electron energy spectra, and this instrument is developed by IRAP in France. And talking about low energy electron measurements at Mercury, only partial electron measurements were made on board Mariner 10, since the protective cover of the sunward-facing electrostatic analyzer did not open fully after launch. And the messenger mission which has the first one to orbit the planet, did not have a low-energy electron spectrometer on board. So MESSENGER made limited indirect measurements of electrons using gamma-ray neutral spectrometers or X-ray spectrometers. So this means that MEA will provide new and unique measurements at Mercury. And this figure shows the cross-section of MEA analyzer. And what is special for this MEA is MEA has variable transmission characteristics. And there is inner sphere and outer sphere, and electrons come into this way. And by applying high voltage to the inner sphere, only appropriate energy electrons can pass through this analyzer gaps. And there is a detector here and detected by this MPPE. And the inner sphere is divided into two parts, as you can see. And by applying different voltage to the top part and analyzer part, we can change the sensitivity of the analyzer electrically. And right-hand side figure shows this. And usually the top part and analyzer part is applied the same voltage. And in this case, the geometrical factor, that is sensitivity, is around here. But the ratio between top part and analyzer part voltage is changed. The sensitivity becomes lower, as low as 1% of the original sensitivity. So this is new for this instrument. And this table shows the summary of MEA performance. And its field of view is 8 degrees times 300 degrees. So this is the ring-shaped field of view. And angular resolution is 22.5 degrees times 11.25 degrees. So 306 degrees are divided into 16 sectors. And energy range is 3 eV to 25.5 keV in Mercury mode, and 3 eV to 3 keV for solar wind mode. And energy resolution is 10%, and time resolution is 2 seconds using a single analyzer, and 1 second using 2 analyzers. And geometrical factor is shown here. And 2 MEA analyzers, MEA1 and MEA2, has different geometrical factor. And each instrument, it can be changed using the electrical control. And looking at this, the lowest geometrical factor is 1 times 10 to the 6, and the largest geometrical factor is 1 times 10 to the 3. So 1,000 dynamic range is realized using 2 instruments. Okay, and talking about the data products of low-energy electrons, depending on the MPP mode I explained before, and depending on the L mode, M mode, H mode data, several kinds of data are obtained. One is 3D full distribution function and omnidirectional energy spectra, and pitch angle distribution for selected energy and velocity moments. And as you can see, the highest time resolution obtained by each instrument is 2 seconds. And combining these 2 instruments, the highest energy will be as high as 1 second. Okay, next is MIA. And this instrument is a toroidal electrostatic analyzer with electrical sensitivity control. And it measures ion energy spectra, and it is developed in ISSIS. And I'm responsible for developing this instrument. And this figure shows the cross-section of MIA instrument. And as we can see, this is the similar structure as MEA, but the inner sphere is not divided into 2 parts. But instead, by applying high voltage to this top part, this analyzer also can change the sensitivity electrically. And we can see some light traps here to prevent the noise generated by the solar light. And there is an MPPE here, so ions are coming in this way, and applying voltage to the inner sphere, ions with appropriate energy can pass through this analyzer and detected by this MPPE. And what is new in this instrument is that we are using MPPE anode with ASIC. That is shown here. This plate detects the magnified charged cloud, and behind the backside of this plate, ASIC is installed. That is 5 millimeter size, And inside the ASIC, 64 channels, preamplifier, and counters are included. So it contributed to the reduction of the resource of this instrument. And also, in order to realize the wide dynamic range, mechanical attenuation grid is installed at about 1/3 of the analyzer in that part. And by using this grid installed part, intense solar wind flux is observed. And this figure shows the performance of MIA. This is also a little bit complicated. This is a little bit complicated. But you can see that this is a sensitivity geometrical factor. And when the electrical sensitivity control is off, and with mechanical attenuation grid and without mechanical attenuation grid, and electrical sensitivity control is on, and mechanical attenuation grid with and without, the sensitivity is different. And looking at this, the lowest geometrical factor is 2.81 times 10 to the 7th, and largest one is 4.64 times 10 to the 4. So in this instrument, also 1,000 wide dynamic range is realized using only one instrument. And energy range is 15 eV per charge to 29 kV per charge. And time resolution is with energy step 32, 4 seconds to obtain three-dimensional distribution function. Okay, and talking about the data product of MIA, in L mode, this is a 24 continuous data. We can have 4-second time resolution velocity moments, including density, velocity, and pressures, and also 4-second time resolution ET count data and 4 direction 16 energy. And in case of M mode data, 25 of all the period time is available. The time resolution is 4 seconds to obtain 3-dimensional count data for solar wind, and also 4-second time resolution 3-dimensional count data for all the direction is obtained. And talking about H mode, this is available for only limited period. We have full 3-dimensional count data with time resolution as high as 4 seconds. Okay, and next I will talk about MSA. This is mass spectrometer, and this is a toroidal electrostatic analyzer and EDF time of flight mass spectrometer with electrical sensitivity control. And this instrument measures mass identified ion energy spectra, and this is developed by ISSIS and LPP in France, and MPS and IDA in Germany. And you can see this photo of this instrument here. And this analyzer part is provided by LPP in France. And the bottom side, we have a high voltage power supply. This is provided by MPS in Germany. And back side, we can see CPU and amplifier board. And CPU is provided by IDA in Germany, and amplifier board is provided by ISSIS. So this instrument is developed internationally. And this figure shows the cross-section of this mass spectrometer. And at the top, we can see the electrostatic analyzer. This is the classical spherical energy analyzer. And ions come this way and pass through this analyzer by, only the appropriate energy, ions with appropriate energy can pass through this analyzer. And there's a zinc carbon foil here. And when the ions collide with this carbon foil, by accelerating before entering into this mass analyzer part, the secondary electrons are emitted, and also these entered ions are converted to ions or neutrals or negative ions. And ions are reflected by the electric field inside this mass analyzer part, and the intensity of the electric field is proportional to the distance from the carbon foil. So the motion of these positive ions is the motion of the spring is the same as the motion of the spring. So a high time resolution high mass resolution measurement is possible using these ions. And the neutral particles go straight to the bottom part and detected here. And these particles are also used for mass analysis. But comparing these reflected ions measurements, the mass resolution is lower, but sensitivity is higher. So this is the principle of this instrument. And this table shows the performance of MSA, mass spectrometer. And field of view is 5 degrees times 217 degrees. And angular resolution is 5 degrees times 11.25 degrees. And energy range is 1 eV per charge to 38 keV per charge. And energy resolution is 8%. And mass range is 1 to 60. So this is hydrogen to ions. And mass resolution is m over delta m is 40, lower than, for ions lower than 15 keV per charge. And for ions higher than 15 keV per charge, the mass resolution is 10. And time resolution to measure three-dimensional mass resolved ion distribution function is 4 seconds at the fastest case. And in using 6400 steps, it takes 8 seconds. And geometrical factor is 7 times 10 to the third and 5 times 10 to the fourth. And the geometrical factor, the sensitivity can be electrically changed. Okay. And talking about the MSA data products, well, depending on the N mode and M mode and H mode, we have several data products. And this is quite complicated. But looking at the time resolution, we can have 4-second time resolution velocity moments for protons or alpha particles or heavier ions. And talking about the medium data, we have several data modes. For different data modes, for example, the protons data can be obtained 24-second time resolution, and heavier ions it can be obtained 256 seconds, and so on. And for other data modes, high spatial data modes, we can have the proton data in 16 seconds and heavier ion data in 256 seconds. But using the high temporal mode, we can have protons in 8 seconds and heavier ions in 64 seconds. Okay, so these are the data products obtained by mass spectrometers. And the next one is HEP electrons. This is a pin slit type collimator and a solid state detector with ion rejection foil. And this measures electron energy spectra, and it is developed in Japan, ISSI and Nagoya University. And another high energy particle sensor is HEP-ion. And this is a conical collimator plus time of flight unit plus SST instrument. And it measures high energy ion energy spectra. And this instrument is developed in ISSI and Nagoya University in Japan. And this figure shows the cross-section of HEP electron analyzer. And this figure shows the structure and field of view of HEP electrons. And you can see these two detectors. These are the solid-state detectors. And these are two assemblies of aluminum-coated detectors. And there is a pin slit here, and electrons enter into this analyzer through this pinhole. And this instrument has two field of views, and one is upper field of view, and this is 11.4 degrees divided into 5 directions. And the lower field of view also has 11.4 degrees field of view is separated into 5 sectors. And about the center part, because a strong solar light enter into this part, so there is a sun shield here. So there is a dead angle of plus minus 8 degrees in the center part. And this figure shows the structure and measurement principle of HEP-ion detectors. And incident particle come this way, and there is a thin carbon foil here. And when ions, high energy ions, pass through this carbon foil, secondary electrons are emitted, and these electrons are detected at start timing. And the ions pass through this thin carbon foil, fly this way, and collides with this solid state detector, and energy is measured. At the same time, the secondary ions are emitted from the surface and detected here as a stop signals. And using the energy detected by this SST and measuring the time difference, the another information is obtained, and using these two information, we can detect the mass and energy of this incident particles. And what is new in this instrument is that this instrument uses single-sided silicon strip detector, SSSD, with ASIC readout system. ASIC is called VA32TA. And 158 strips for 5 ASICs are shown here. And pulse height sums for adjacent 3 strips corresponding to the incident energy, and location of signal strips corresponding to incident angles. Okay, and this table shows the sensor characteristics of HEP electrons, and energy range is 30 keV to 700 keV, and energy resolution is at 30 degrees 16 keV, and at 60 degrees 20 keV. And field of view is 20 degrees times 57 degrees times 2, and 57 degrees are divided into 5 directions, so the angular resolution is 11.5 degrees. And time resolution is as high as 1 spin, so this is 4 seconds. And HEP electron data product is shown here. For L mode, polar direction is divided into 2 directions, and spin sector is divided into 4 sectors, and energy step is 3. These data can be obtained in 60 seconds. And in M mode, polar direction is divided into 10 directions, and sector is divided into 8, and energy step 4, this data is obtained in 4 seconds, and in high mode, the higher angular resolution data are obtained in 4 seconds. And this table shows the sensor characteristics of HEP ions, and the energy range is 50 keV to 1.5 MeV, and energy resolution is 60 keV at 30 degrees and 20 keV at 60 degrees, and field of view is 11 degrees times 70 degrees times 2, and so this 70 degrees is divided into 3 directions, so angular resolution is 23.3 degrees. And the time of flight measurement resolution is 1 nanosecond. Okay, and HEP ion data product is shown in this table. For L mode and M mode, the energy analysis is made in 60 seconds, and polar direction is divided into 2, and spin sector is divided into 4, and energy steps are 4. And for M mode, 6 by 8 polar and sector directions, and energy steps is 8. This data is obtained in 4 seconds. And talking time of flight analysis data, in L mode, this data is obtained in 60 seconds, and for M mode, this data is obtained in 4 seconds. Okay, so these are the data products of HEP ions. And the next one is ENA. ENA is an energetic neutral atom analyzer, and it will measure the global structure and dynamics of the magnetosphere, and magnetosphere surface magnetosphere exosphere interaction process is the target of this instrument. And this analyzer measures mass-identified ENAs, and it is developed in by IRF Sweden and ISSI Japan, and University of Bern in Switzerland, and IRAP in France. And this figure shows the principle of this instrument. And in the inlet part, there is a deflector here, and ion is direction, and angular collimation is made here. And next is conversion surface, and this conversion surface ionized the incident neutrals. And ionized particles go through this electric guide, and this function as the photon direction and energy analysis. And it collides with the start surface, and secondary electrons are emitted and used as start MCP and start pulse, and the reflected ion particles are directed by stop MCP, and the signal is used for stop signals. And using these signals, velocity analysis and detection using time of flight constant system is shown here, and these measurements are made. Okay. And performance of this ENA sensor is shown here, and the energy range is 10 eV to 3.3 keV, and energy resolution is 100. and mass resolution is H, hydrogen, helium, and oxygen, and sodium, magnesium groups, and potassium, calcium group, and ions. And angular resolution is 9 times 25 degrees, and angular pixels is 7, and field of view is 15 degrees times 160 degrees. And time resolution is 4 seconds in the fastest case. Okay. And the observation plan of ENA is shown here. ENA uses only L mode data, and ENA can be on continuously except for the period when the instrument should be off. For example, survival for several thermal conditions near aphelion, severe thermal condition near aphelion. And on average, telemetry budget seems to allow these modes in case of continuous measurements. The energy is 8 steps, and angular resolution at 20.5 degrees, 22.5 degrees times 25 degrees, and mass is 3 to 4 beams, and time resolution is 32 to 64 seconds. So this observation will be made around Mercury, in Mercury orbit. And high resolution mode for time and mass will be considered to be used in the near perihelion and near apophelion periods. Okay. Okay, so using the 7 sensors, including 2 MEAs and HEP electrons and ions, each instrument is covers these science objectives. And by using all the data obtained by these instruments, we'd like to make comprehensive measurements of Mercury magnetosphere. And I'd like to say that we are now conducting the 25-year quest for plasma environment around ALS bodies. And the plasma measurement is studied from the observation of Earth's environment, including ionosphere and magnetosphere. And as the spacecraft go further to the solar systems, the observation region of the plasma is also expanding. And in our solar system, there are several planets with different boundary conditions and different solar wind parameters. And for example, Mars and Venus are non-magnetized planets. On the other hand, Jupiter is strong with the planet with strong magnetic field. And another category of the planet is with air or without airs. And Moon and Mercury is a typical planet, typical heavenly bodies without air. So these Moon and Mercury are airless bodies. And Moon has no global magnetic field and no air. And on the other hand, Mercury has a global magnetic field, but it doesn't have air. So, we visited the Moon in 2007 by Kaguya spacecraft with our plasma instrument. And in 2025, we are going to visit Mercury by BepiColombo with our plasma instrument. So we are now conducting this plasma environment, 25-year quest for plasma environment around ALS bodies. And talking about the Moon plasma environment was simple. And most of the plasma behave as MHD plasmas or single particle, except for the area around magnetic anomalies or wake boundaries. Because the size of many magnetic anomalies on the Moon is similar to the size of ions, scale of ions, the area around magnetic anomalies is interesting from the viewpoint of plasma physics. And solar wind Moon surface interaction is also quite interesting. That generates lunar surface origin heavy ions. And talking about the Mercury plasma environment, it seems to be much more complicated than that of the Moon due to the existence of global intrinsic magnetic field. And it means that Mercury plasma environment is very interesting from the viewpoint of plasma physics. And the understanding of the simple process found at Moon can be used to understand the plasma process to be found at Mercury. And the knowledge about solar wind Moon surface interaction can also be used for understanding the similar process occurring at Mercury. So I'm very happy to be able to participate in 25-year quest for airless bodies, including 2 missions to airless bodies, Moon and Mercury. And taking steps we will be able to understand the plasma processes around airless bodies in general. And the first step was to understand simple Moon, and the next step is to understand more complicated Mercury. Okay, and this slide summarizes what I learned from the development of MPPE. Development of instruments forming an international team is very exciting, and I learned many things from our international team members. And if each participating team possesses the similar level of technique or experience, the result of the interaction will not be simple sum, but multiplication. And planetary exploration takes a very long time. Well, I started to participating in this BepiColombo project about 15 years ago. And some of the initiating members have already retired and passed on their roles to the younger generation. And it will be quite important to keep adding young members in the team to make the most of the obtained data in the future. And we are enjoying participating in PP-related meetings held in multiple places. And so I sincerely hope that the COVID-19 infection problem will be resolved in the near future. And we have some more time, so I will show a little bit about the Earth flyby observation and Venus flyby observation data of MPPE. And Earth flyby observation was made between September 4th and November 4th last year. And this figure shows the orbit of the BepiColombo around Earth, and it entered into the Earth's magnetosphere from the solar wind and crossed the bow shock and crossed the magnetopoles and entered into the magnetosphere and passed through the radiation belt and go into the magnetosphere and go to the sheath and went outside to the solar wind. So during this time, we made observation by powering on MPP instruments. And this figure shows the ET spectrograms of electrons obtained by MEA1 and MEA2 instrument. And this panel shows the ion ET spectrogram measured by MIA. And this panel shows the high energy electron flux obtained by HP electrons. And this bottom panel shows the solar particle monitor data. And as you can see, we have observed the solar wind electrons and these magnetosphere ions in the plasma sheet. And also we measured these sheath ions. And also the HEP electron detected the high energy electrons here below 190 keV. And inside the radiation belt, the solar particle monitor detected these high energy particles. And ENA also detected some particle counts. And this is the ENA, 7 channels of ENA, and this horizontal axis is the time. And well, channel 4 shows some counts of detected by ENA, but these counts may be generated by a solar wind impact on the thermal shield of the BepiColombo spacecraft. Okay, so anyway, this ENA instrument also functioning very well. And Venus flyby data is shown here, and this red line shows the orbit of the BepiColombo spacecraft on Venus, and the spacecraft crossed the bow shock and also went into the tail region of the Venus like this. And during that period, the electron data is obtained like this, and ion data is obtained like this. And these two panels show the plasma wave instruments data. But anyway, the instruments are functioning very well. And this is the enlarged version of the electron and ion data. And electron data shows this panel, and ion data is shown this panel. And we observed the ions and electrons in the Venus tail regions. And also ENA detected these counts as before, and this may be generated by solar wind impact on the this thermal shield. And also HP observed some modulation of the high energy particles before crossing the bow shock. Okay, so by making these observations, we can say that the cruise phase plasma particle data so far obtained prove that MPPE or MEA is capable of making comprehensive measurements of plasma particles with high quality when MEA arrives at Mercury in 2025. Okay, so this is the last slide of my presentation. And this figure table shows the future flyby events. So we will have second Venus flyby August this year and first Mercury flyby October this year. And every year we will have Mercury flybys, and we will arrive at Mercury in December 2025. And thank you very much.
Thank you very much. Can you hear me?
Mm-hmm. So are there questions to Professor Saito?
Yes, we have some questions. I will send them in the chat. The first one for Professor Saito is, would energetic ions also contribute to the X-ray aurora?
Well, I'm not sure, but major source will be electrons, ions electrons. But there is some possibility that ions are affecting something. Okay, so we'd like to figure out what is happening there in the future.
Okay. I see there is this incoming question, comment from Junjong. Thank you for the impressive talk. And then the question, in Mercury's magnetosphere, the density of cold planetary ions may be much more than previously thought. That was missed by messenger FIPS detection. Thanks to the MPPE instrument, we can detect these cold ions from 1 to 10 eV in the future. Would the spacecraft charging potential affect the measurements of these cold ions, such as ion flux and their actual direction?
Yes. When the sunlight illuminates the spacecraft will be charged up to the positive voltage. And when it is in the eclipse, the spacecraft is charged up to the negative voltage. But thanks to those potentials, well, because the lowest energy of this low energy analyzer is several eV, but if when the spacecraft is inside the eclipse and spacecraft is negatively charged up, very low energy ions can also be measured by these low energy ion sensors. And also, it is the same for electron sensors, low energy electron sensors. In the in the sunlit regions, the spacecraft is positively charged up. So in that case, very low energy electrons can be measured.
Thank you very much. We have another question. Of course, in the meanwhile, everyone can submit their question either here on Bilibili. The next one is, should the reconnection processes at Mercury be different from those of the Earth, since Mercury has no ionosphere?
Yes, that's what we want to solve in future using MPPE observations. Well, the messenger spacecraft found that the substorm phenomena is Earth-like. The difference is, well, the time duration of the substorm-like events. But for the detail, we have to make measurement using all the MPP sensor data, and we'll be able to do that because we are going to make comprehensive measurements of the plasmas. So we want to solve this in the future.
Thank you very much, and also thank you from Grundong. And then, what is the most difficult part of your very sophisticated instrument?
Well, because the Mercury is very hot, so very hot, and the solar light is solar UV intensity is very high. It is about 10 times higher. So we have to well design our instrument in order to reject those solar UV as much as possible, and also the our analyzer has to be operated under very hot temperature. And in order to do so, we have to select the detectors carefully, and also the thermal design should be carefully made. So that is the difficult point.
Thank you very much. Then there is a question from Zhao Jinrong. Why are 2 spacecraft needed by the BepiColombo mission? What can we do by combining MMO and MPO?
Okay, there are many things can be done using 2 spacecraft. Talking about the particle measurement, well, the MPO spacecraft also has particle instruments, and it also has the mass spectrometer for neutrals. And for example, in order to understand the sodium or heavy atmosphere of heavy ion components or heavy particle components, the MPO measures the, for example, neutrals, heavy ions and neutrals coming from the surface, and those ions or particles or ionized particles are accelerated by some mechanisms, and at the position of the MMO spacecraft, the accelerated particles can be measured. So the 2-point measurement is very important to understand the particle acceleration mechanisms and the generation mechanism of the heavy particles. So that is one example. And well, there are so many examples such like that. Okay.
Thank you very much. Again, everyone can submit their question in the chat box, both here or on Bilibili. In the meanwhile, while we wait for any eventual further question, I would like to thank you once again, Professor Saito, for accepting our invitation and for this excellent talk that was recorded as usual, and we will upload it tomorrow on our social media channels and on our website. So in case you missed part of it or the presentation, you can always rewatch it from tomorrow on. I see no further incoming question. If Professor Heap doesn't have anything else to add, we can.
I just want to thank Saito-san for a very clear and excellent presentation, and I think he's going to get excellent results from his instrument at Mercury.
Okay, thank you very much.
So thank you very much once again. I would like to remind everyone that our next On Things to Come talk will be next Wednesday, April the 14th, with Daniel Mueller from the European Space Agency, and it will be on their Solar Orbiter mission. It will be the first one of a couple of talks on the Solar Orbiter. And on Monday night at 8 p.m. Beijing time, we will have a 1001 Space Nights, which we from the Macau University of Science and Technology. So thank you very much once again, Professor Saito, and to all participants, and hopefully see you next week. Thank you.
Thank you very much.
Bye-bye.
Bye-bye.